This lesson will introduce seasonal autoregressions. In order to fully understand seasonal autoregressions, and in fact later to understand seasonal moving averages, it's necessary first to introduce the lag operator. The lag operator is discussed in the notes, but we didn't spend a lot of time on it in the course. It's going to be used a lot to actually describe the seasonal autoregressive structure. So lag operator is an operator, but it's written L, and it has a few key properties. First, the lag operator applied to xt backshifts or lags xt. So L of xt is xt minus 1. The lag operator can be multiplied by itself, so L squared xt, which is just L of Lxt, which of course we see Lxt can be written as xt minus 1, but we have another lag operator there, which just adds another backshift or another lag, and so L squared of xt is simply xt minus 2. And finally, if we have the product of two different powers, L to the p, L to the q, this is simply L to the p plus q, and when applied to xt, it simply lags xt by p plus q values. There are a few other properties that are discussed in the notes of the lag operator, although we're not actually going to use any of them here, and so we'll omit them. We can actually see how they work with some models that we've seen before. For example, I start with an AR1, so we have xt, depends on a constant phi naught, AR1 coefficient phi 1, and xt minus 1. To write this as a lag polynomial, we start by moving the autoregressive term to the left side. That gives us xt minus phi 1, xt minus 1. I then pull out the lag operator to get phi 1 times L of xt minus 1. So I have xt minus phi 1 L xt. So in other words, I can actually have an xt that I can pull out separately. And so I have 1 minus phi L times xt equals phi naught plus epsilon. So in other words, we actually have written the AR1 with a very simple lag polynomial, it's called. That is, it's a simple degree 1 polynomial in L that has xt. Lag polynomials, of course, can be used for higher order autoregressions. So if we look at the very bottom, we have an ARP. So we have phi 1, xt minus 1, phi 2, xt minus 2, all the way through phi p, xt minus p. If we want to write this with lag operator, we of course simply shift all these to the left side. Then we factor out the lag. But the one thing we're going to see is that, of course, these lags are going to have different powers. So the first one is just going to be phi 1 times L, because it's going to backshift xt by 1. Of course, there is a 1 hiding there. We then have phi 2 times L squared, because we need to shift xt by 2. Finally, through phi p, we have L to the power p, which will backshift xt by p. So again, this is also what we call a lag polynomial. And in this case, it's going to have an order higher than 1. It's going to order p polynomial. But nonetheless, everything is working the same. And so we can see that this lag operator allows us to write models based on polynomial representations. So far, this doesn't actually bias much. But when we see seasonal models, it will help us understand the structure of them in a much better way. So to understand seasonal models, we'll start by a pure seasonal AR model. So a pure seasonal AR model is going to evolve with a coefficient that has a seasonal component to it. So instead of just looking at, say, 1 minus phi to the power L, which would be a first order autoregression, we're now going to have L raised to the power M. So in other words, when I multiply that by xt, so when I have L to the power M xt, this is going to give me xt minus M. And again, remember, M is the seasonal period of our series. So for example, monthly data, M would be 12. This pure seasonal AR, when you write it in the form that we're more familiar with, would have xt be a function of a constant and a single coefficient, phi m, multiplied by xt minus m, or m periods ago. So while this model is very simple, it's not actually plausible. It's not actually plausible because if you had a process that evolved like this, it would essentially be m independent AR1s, where you simply would have an AR1 that would be xt and xt minus m. You'd have another one that would be, say, xt plus 1 and xt minus m plus 1, all the way through xt plus m minus 1 and xt minus 1. So each one of these, in fact, would be a totally unrelated AR1, and so this series would have particularly chaotic dynamics. In practice, this is not something you normally experience, so when you want to include a seasonal AR, you always want to include a standard AR. So that is, we need to have short-run dynamics, and what the short-run dynamics do is they actually link together these seasonal components so that they become more coherent and they don't sort of deviate and have sort of arbitrary movements between each other. The way we do that is we're actually going to use the lag operator again in these polynomials, except now we're going to have two. So first, we are going to have the seasonal component. So we have phi to the m, L to the m. That's exactly what we had above. But then to that, we're going to add a short range component. That is, in this case, we just have an example with a first order AR. But to see what the model actually looks like, we need to expand the polynomial by multiplying these two terms together. When you multiply these terms together, we're actually going to get four distinct terms. So we have 1 minus phi 1L, that's going to be my AR1 term, minus phi m to the L to the m. This is going to be my, you can think of it as ARM term, that's my seasonal term. But we also get an additional term, phi 1 times m1, L to the power m plus 1. And this is a natural thing that happens when you have two roots evolving at very different frequencies. So you end up with a third term that comes from these. And this third term is an essential feature you see in seasonal autoregressive models. So we actually write this in the form that we're most useful with. That is, we sort of just multiply out the lag operators times x. We're going to xt, depends on a constant, the AR1 term, what looks like the seasonal term, but then there's going to be an additional term. The coefficient on this term, however, is not free. The coefficient on this term, as you can see, is phi 1 times phi m. That is, it's the same as the coefficient on xt minus 1 times the coefficient on xt minus m. And so this is something that needs to be done when you model a seasonal autoregression. And so in fact, this is what we'd call restricted AR m plus 1. It's restricted in two ways. First, there's obviously a lot of terms missing. There's no phi 2, phi 3, all the way through phi m minus 1. So this entire range of terms are not there. Again, that's more of a modeling choice, whether you need sort of additional short-run dynamics or not. But the other restriction that is more important and certainly non-trivial is that the coefficient on xt minus m minus 1 is in fact the product and the negative product of phi 1 times phi m. So that is a required feature of a seasonal autoregressive model. That's not something we've seen before, and in practice it will complicate the estimation of these. In terms of notation, sometimes this is called a seasonal autoregression 1 cross 1, where the first one is the short-run dynamics, and the second one is the seasonal. More generally, you can have a seasonal autoregression P, short-run dynamics, with a different P for the seasonal dynamics. In practice, seasonal dynamics are usually kept very small, simply because they operate on a relatively large lag. So for example, with monthly data, where your seasonality is 12, then every time you add a seasonal autoregressive lag, you're going to actually have to go back 12 observations. The second one would be 24 observations. And so you end up with a model with a relatively long lag structure very quickly if the seasonal autoregressive is in fact more than one. So it's common to limit seasonal autoregressives, especially when they're needed in forecasting models, to a single seasonal lag. A useful thing to do in many cases, especially when just interested in forecasting rather than trying to get a really coherent model, is to just ignore the restriction. So we see before, obviously, that we had xt minus 1, xt minus m, and xt minus m minus 1. So these are the terms that naturally appear in a seasonal autoregression 1-1. But we saw in the previous model that the phi m plus 1 term, in fact, should respect this restriction to be minus phi 1 phi m. However, this is something that we don't have to impose. If it's true, then we would expect, at least in large enough samples, for these coefficients to be very close. You could actually test this. We won't talk about how you would test that. It's a nonlinear hypothesis test. We've only really focused on linear hypothesis tests in the course. It's not particularly difficult. It uses what's known as the delta method. It's in the notes, chapter 2 if you're interested. But it's not essential for us, and we're not particularly going to try to test it. What's important here is that this model, of course, is equivalent to the seasonal model. In fact, it's more general. If the seasonal model is misspecified, then this phi m plus 1 term could take a value that's different from phi 1 and phi m. It's also, of course, much easier to estimate because it's just a standard OLS. There's nothing to do. When you impose the restriction, where you have this product term, that is phi m plus 1, has to be equal to minus phi 1 phi m, then we have to estimate the model using an alternative method, for example, nonlinear least squares, or in many software packages, they actually use maximum likelihood estimation. So it certainly adds a non-trivial complication in terms of estimation and the ease of model estimation when you want to do this, because as long as you're in this sort of OLS case, it's very simple to include time trends, seasonal dummies, Fourier, and seasonal AR with no restriction. All of that can be done inside an OLS, which means that sort of building, estimating, testing time series models with all of these features is extremely simple and fast. And this is in some senses certainly the more common approach than formally allowing for the restriction to be imposed, which requires a nonlinear optimizer, which adds some difficulties, especially when producing a lot of forecasts across many series or many time periods, that things can go wrong or things might not work as expected. In autoregressive models, prediction intervals are not constant. So far, we've seen that prediction intervals were constant when we have time trends or seasonalities, but once we allow a cyclical component, we're not going to get constant prediction intervals. That's simply because when we have, say, autoregressive terms, we're going to have a buildup of errors. That is, the one-step ahead forecast error is actually going to show up in the two-step ahead forecast error, not one-to-one, but with some reduction or some smoothing. So we need to actually compute it. And so now the prediction intervals we're going to have are in fact going to have a term that depends on h. So it depends on the horizon. It also depends on the model parameters and, in fact, the model specification. The way we actually compute it is we use what we saw before as the MA infinity representation. So we saw this a few times. The most recent time we saw this was when we looked at vector autoregressive modeling. We saw how we can get the MA infinity representation for a vector autoregression using what's called the companion form. So we want to use the companion form of an ARP. That is, we can simply write xt minus 1, all the way through xt minus p plus 1 as a function of lagged values of that, just lagged 1. So the first one is xt minus 1, then xt minus 2, all the way through xt minus p. We then have the autoregressive coefficients showing up in the first row. So we have phi 1, phi 2, all the way through phi p. Then every other term in the model is just 1 or 0. And this is simply because we know that xt minus 1 is exactly equal to xt minus 1. We don't really care about the error structure here in the companion form, but you can see that the first one is epsilon and the rest, of course, are 0 because xt minus 1 equals xt minus 1 with no error. So this is what we call the companion form. We saw it for vector autoregressions, but of course an AR is just a special case of a vector autoregression with a single series. This is useful because once we have this first order vector autoregression now, even though we have an ARP, can be written as a first order vector autoregression, we now can easily derive the MA infinity representation, which has coefficients. In fact, the first one, which is missing, is just phi to the power 0, or an identity matrix. Then it has phi, the matrix phi squared, should be phi cubed here, should be power 3 there, typo, and so on. So that's very easy to do, and this is sort of something we saw in the context of vector autoregressions. We called these, in fact, xi's, and these were exactly the matrices we needed to compute when we wanted to look at impulse response functions. And in fact, the prediction intervals are actually going to depend on the coefficients of the impulse responses to the autoregressive model. To actually get the impulse responses, we just need to look at the 1 element of each of the xi matrices. That's going to be the one that corresponds to the process in sort of the most recent period. And we get these 1 elements, and then when we want to get the variance for h periods ahead, it's going to depend on the variance of the residuals, sigma squared. And then finally, plus 1 plus xi1 squared plus xi2 squared, all the way through xi(h minus 1 squared. So it has a particularly simple form. Once you have these xi's, of course, getting these xi's is not particularly difficult. The mathematics behind it are in the VAR slides and in the VAR notes. But, let's just assume we can get it. In the AR1 case, it's extremely simple to derive. That is, of course, we know the AR1 case, these coefficients are simply going to be phi1. The coefficients for these xi's are going to be phi1 squared, phi1 cubed, and so on. So these are going to be this is going to be this xi1, xi2, xi3. So we need to square each one of these terms. You can see there's a square on each one of those terms, and so it's necessary to square those. But once we've squared those, we're simply going to get phi1 squared, phi1 4, and phi1 to the 2h minus 1. So this is what we get in AR1. In an AR2 or in a seasonal autoregression, it's going to be more complicated, but there's nothing particularly difficult about computing it. And ultimately, these allow us to construct prediction intervals, again, making an assumption of normality using a very simple expression, which is just plus minus 1, the forecast plus minus 1.96 times now this particular structure for the forecast error variance. Just like we know for usual autoregressions, when the coefficient equals 1, we get what we call a unit root. It's possible for seasonal models to also have what's known as a seasonal unit root. This happens when the L term is multiplied by 1. So that is, you actually have a unit root, but not at the first lag, but at lag L. Again, once we include short-run dynamics, again, this should be a lowercase m, it's not anything special there, then we can see that we have short-run dynamics, but then we also have a seasonal unit root there. And so when we have seasonal unit roots, we actually have to use a new type of differencing to remove them called seasonal differencing. That is, we want to look at the season over season growth rather than on the short-term growth. To think of a series where you might actually really seriously want to think about seasonal differencing, you think about sort of quarterly profits of firms. Take a firm like Apple. So Apple is a firm that has a lot of cyclical variation in its profits, and we know that we want to think about whether Apple is doing well. We want to look at year-over-year changes. We don't want to actually look at quarter-over-quarter changes, because when you have Christmas, which is a good quarter for them, and then the quarter after Christmas, which tends to be a bad quarter, there are obviously quarters where they release new iPhones and so on. These quarterly differences lead to some very predictable short-run dynamics that are not really what you'd want to capture. And so we use a year-over-year differencing, which we say quarter over, using 4 quarters difference. And the way we do that is we use the seasonal differencing operator. This is now this delta little m applied to xt, which just takes the difference of xt and xt m periods ago. So to be clear, this delta lower m, it is in fact quite different from delta to the power m. So delta to the power m, which we've seen before, at least for the power 2, is of course delta of delta m minus 1, which in fact leads to a difference of lots and lots of differences. If m is moderately large, like 4 or 5, this actually becomes a very complicated expression of the original x's that depends on something called the coefficients of Pascal's triangle. But if we take the seasonal difference, that is delta lowercase m of xt, it's always just xt minus m. It always involves 2 terms. Just to see what happens when we have a second difference, so we take delta squared of xt. This is something we did, for example, when we looked at the change of inflation. So CPI, difference once to take logs of CPI, difference it once to get inflation, difference it again to get the change of inflation. This, of course, is the difference of the first difference. And so when you actually take the difference of the first difference, you end up with an expression that now will involve xt, xt minus 1, and xt minus 2. This is very different from when we use this if we had a sort of 2-period seasonal difference, that is delta lowercase 2, xt. This is always just xt minus 2. So, you see, in fact, the signs are different. You have these xt-1 terms involved when you take the double difference. And so seasonal differencing is, in fact, different from applying the difference operator twice. So in the previous slide, we talked about seasonal differencing as a way to remove seasonal unit roots. So for example, when we take the seasonal difference of the series xt, if we have a seasonal unit root, so that is the original model is 1 minus phi L times 1 minus, there's no phi there. One minus L to the power m of xt, so we have a seasonal unit root. If we difference it using delta m of xt, then we can apply the 1 minus phi 1L polynomial to the difference. So that is on the left-hand side, we're left with delta m of xt. On the right side, we get delta m of xt minus 1. This comes from the fact that when we have L of delta m xt, this is the same as delta m of L of xt, which of course is the same as delta m of xt minus 1. It's easy to show. So in fact, once we take seasonal differencing, we end up with just a standard autoregression, except now for a different time series, particularly the year-over-year changes, or obviously it depends on the seasonality, but for quarterly or monthly data, it would be year-over-year changes, and it just becomes a standard autoregression that one can then model. Of course, one has to keep in mind that you have done seasonal differencing, because that will matter when you construct forecasts. An important feature of seasonal differencing is that you don't ever need seasonal dummies when you have seasonal differencing. That's simply because if you had a dummy that happened, say, every fourth quarter, then when you take the difference of a fourth quarter and the previous fourth quarter, the level shift is going to be lost. So you won't actually need to include seasonal dummies when you do seasonal differencing. This lesson has introduced seasonal autoregressions, which allow us to capture dynamics at seasonal frequencies. In practice, these have to be combined with short-run dynamics to construct plausible models. Pure seasonal models are not something you would actually expect to see in practice. Unrestricted models that include the same coefficients that we get from the seasonal autoregression can be estimated by OLS, which makes them particularly attractive. Prediction intervals for autoregressions or seasonal autoregressions always depend only on the MA infinity representation, which are in fact just the impulses to the model. Finally, we saw that seasonal differencing is a way to remove seasonal random walks that also removes level shifts in the series, and so we don't need to use seasonal dummies when we use seasonal differencing.